In this video, we will learn how to classify chemical reactions by reaction patterns. Before we begin, it's important that we're speaking the same language. So I'm going to introduce some vocabulary that you might have heard before, most likely heard before, but just to make sure that we all remember so that we're all on the same page. First up is the word acid. Acids, we learned in chapter 3, are compounds that produce H+ ions when they're dissolved in solution. Acids can either be weak electrolytes or they can be strong electrolytes, depending on how much H+ ions they produce in solution. When we're looking at chemical formulas, we are looking for hydrogen to be listed first in the chemical formula as our clue that it's an acid. And so we have, these are examples. HBr is hydrobromic acid. H2SO4 is sulfuric acid. Next up, we have bases. Bases are, we're going to define as any chemical with a hydroxide anion. That's for now. When we get to a later chapter, we will expand our definition of bases. But for now, we're looking for the hydroxide anion. And so both of these are ionic compounds. And so these are ionic bases. And so you can look on your green sheet for examples of strong bases. But all the bases have hydroxide ions in common. Next up, we have hydrocarbons. Hydrocarbons are molecular compounds, meaning they are all nonmetal elements, consisting of carbon and hydrogen. For the purposes of Chem 3A, which is your course, we are going to, the strict definition is it's only carbon and hydrogen, but if you see something that's carbon, hydrogen, and oxygen, it's okay for Chem 3A to still call it a hydrocarbon. Because we're in Intro Chem and we don't need to nitpick about definitions here. Next up, we have salts. Salts are any ionic compound other than an acid or a base. And so we have none of the acids are ionic compounds. All the acids are molecular in some way. But for example, we are still looking for ionic compounds. And so we're looking for a metal with a nonmetal, or a metal with polyatomic anion. So we have, in the examples here, we have calcium chloride and potassium nitrate. Hydrates are salts, meaning ionic compounds, where there's water molecules that fill up the gaps between the ions in a fixed ratio. And so I'm going to write like wet sponges. And so we can dry hydrates by evaporating off the water, and then we can put the water molecules back on by re-wetting it. So just like a sponge can be dried and re-wet. There's a couple different ways that we can classify chemical reactions. One is to look at simple patterns of how the atoms are rearranging themselves, and a different way of classifying chemical reactions is by observable phenomenon, like what we can see with our eyeballs. There is some overlap between these two different categories. When you get onto ALEX, there will be an extra assignment that's not part of the PI. In that extra assignment, you will be practicing counting atoms, practice balancing equations, practice writing equations from words, and I really recommend that you do that assignment before you're working on the topics that are in your PI, because the topics that are actually part of your PI assume that you already know how to do that. Also, you might see some other words in Alex. So if you see single displacement, that means the same thing as single replacement and single substitution. Likewise, if you see double displacement, double replacement, double substitution, or something that's called metathesis, all of those mean the same thing. So you're looking at the keyword there of either double or single, and then they'll interchange what word comes after that. And then metathesis just means double displacement. So before we do examples, I'm just going to define some of these simple reaction patterns. Our first reaction pattern is called a combination reaction. And so in a combination reaction, you will see two different chemical species joined together. So you will see two different things become one thing. A decomposition is the opposite, where you start off with one thing, and then once you get into the product side, they have separated into two separate species that are no longer bonded together. A single displacement is our first reaction pattern where we have three different species. So we see letters of A, B, and C. In a single displacement pattern, A will replace, kick out either B or C and kick out the other one. So it doesn't really matter what letters you choose to use. You could use A, B, and C. You could use A, C, and D, but the pattern still holds true. Which element A kicks out and replaces depends on whether A would like to be a cation or whether A would like to be an anion. Remember that cations are always listed first in the chemical formula, and anions are always listed second. And we'll do an example in a little bit. Our last general pattern of chemical reactions is called a double displacement reaction. In a double displacement reaction, our cations and anions swap places. And so since our cations are always listed first, C will have to bond with F. And E will have to bond with D. So that our cations are forming new products. These new products are commonly called ion exchange products because our cations and our anions are swapping pairs of what they're bonded with. And then several of our observable reaction types fit into this pattern. So precipitation reactions, acid-base reactions, and gas evolution reactions are all going to fall under this double displacement reaction pattern. We have some gas evolution reactions that are double displacement followed by a decomposition. And so that one's a little bit more complicated, but in general, you would apply your double displacement pattern first. Look for a key thing in your ion exchange products, and then identify if the decomposition reaction is going to occur. So let's practice identifying these reaction patterns. Go ahead and pause the video and try to work out which of these reactions are single displacement, double displacement, combination, or decomposition. Okay, if you're continuing on, you must have already solved it and you're here to check your answers. Okay, so for our first one, we have two separate chemical species becoming one. And so that is a combination reaction. Next up, we have aluminum, hydrogen, and sulfate. And then in the product side, we have aluminum bonded to sulfate, and then B is by itself. And so that is a single displacement. Here we have two separate things, A and B, bonding together. And so that is another combination reaction. Here we have one thing, and then it's splitting apart. It's splitting apart a little weird, but the carbon is over here, even though the oxygens get rearranged. And so this is a decomposition. We started off with one thing and we ended up with two things. For our last one, we have sodium bonded with sulfate and silver bonded with nitrate. And in the end, we have silver bonded to sulfate and sodium bonded to nitrate. And so since we have our cations and anions swapping pairs, this is a double displacement. All right, so I said that some observable phenomenons fall under this double displacement reaction pattern. And so we can use our solubility rules that we learned about in chapter 9 in order to identify whether some substances are solids or liquids, or aqueous, I should say. Solids or aqueous. And if it's a solid, it's a precipitation reaction. If all of the products are aqueous, then we don't have a reaction at all. So I'm going to write, so maybe that was a bad placement with the arrow, but all right, all products aqueous equals no reaction. And I'm going to write solid formed. And so if a solid forms, it's precipitation. So let's do our cation swap in order to figure out the products of this chemical reaction. First, we have to identify what ions make up these compounds. Let's start with the anion. Nitrate has a charge of 1 minus. If I have 2 nitrates, that's an overall 2 minus charge. I have 1 lead, and so that has to be lead 2 plus. Sodium has a common ion charge of +1 because it's in group 1. Sulfur has a common ion charge of 2 minus because it would need to gain 2 electrons in order to have a noble gas configuration. And so I need to bond my sodium with my nitrate, and I need to bond my lead with my sulfur. And so in my chemical formulas, let's just focus in on the ions. Both the sodium and the nitrate are 1 minus. Well, there is 1 plus and 1 minus, and so I would need one of each in order to have a neutral ionic compound. And then my lead and my sulfur are both, that's a 2 plus and that's a 2 minus, and so if I have one of each, then I have a neutral ionic compound. And I'm sure you're paying attention to these subscripts here. Those subscripts were necessary for those chemical formulas to be neutral. But these are the neutral chemical formulas for the products. We need to now balance our equation to make sure that we have the same number of ions on each side of the equation. I can do that by putting a 2 coefficient in front. I do not want that 2 coefficient as subscripts. Now I can look at my solubility rules. When you're looking at your solubility rules, find your anion first, and then read across to see if there's any exceptions. Nitrates are usually aqueous, and there's no exceptions to that. Lead sulfate, that's not lead sulfate, that's lead sulfide. Lead sulfide is a solid. It's insoluble. Next up, we have acid-base neutralization reactions. Acid-base neutralization reactions are double displacement reactions where your products are salt and water. And so we're trying to swap our cation and anion pairs. And so here we have an acid. You see the H listed first in the chemical formula. And we have hydroxide, which is an indicator that we have a base. And so if we figure out our ions, we have H plus ions, nitrate anions, hydroxide anions are always 1 minus. And so I need to bond my sodium to my hydrogen. I need to bond my hydrogen to my water, to my hydroxide. But H bonded to OH. So if we did HOH, that's not written as HOH. That is written as H2O. And so if you ever find yourself writing HOH, you have to recognize that hydrogen hydroxide is water. And so you should be writing water. And then for my sodium bonding to my nitrate, that sodium has a +1 charge, nitrate has a 1 minus charge, and so I need 1 of each. And so our reaction pattern is then acid plus a base equals salt and water. Acid-base neutralization reactions, it might look like nothing happened, but heat will be evolved when you mix the two together. So you can draw heat coming off there. Feel the warmth. These are exothermic reactions. For our gas evolution reactions, you will do your double displacement reaction pattern, but you have to recognize that some ion exchange products are either gases or will decompose into gases. And so here we have ion exchange products that will decompose. This one, the H2S, is just a gas. And so that one doesn't decompose, that one's just a gas. So if you see H2S, you have to know that its state symbol is gas. These other ones, how you can figure out what they decompose into is by doing a little bit of subtraction. All of these make water plus some gas. And so if we come up here, we have H2CO3, and let me subtract water. And so 2 hydrogens, subtract that away. 3 minus 1 is 2. And then 1 carbon. So my gas is carbon dioxide. Next up, I have H2SO3. Let me subtract water. Subtract 2 hydrogens away. No hydrogens left. No sulfur cancels out. We have 3 oxygens minus 1 oxygen. That's 2 oxygens. Then we have NH4OH. And then we have to subtract water. And so I didn't subtract any nitrogens. There's a total of 5 hydrogens. I'm subtracting 2 of them. And so there's 3 hydrogens left. So if I regroup that into a 5, and then I subtract, and then you can see that it's 3 left. And so my gas is ammonia gas. All right, how about you pause the video and give your chance the opportunity to practice predicting the products for these examples. All right, you have answers? Let's go ahead and go over this. Before we predict the products, we should identify what reaction pattern we think it's going to follow. And so I see AB plus CD. And so this is a double displacement pattern. Both of these are double displacement patterns. And so that means after I do my pattern, I'm going to have silver bonding with chlorine and potassium bonding with nitrate. But before I write down the chemical formulas of those products, I should identify the ions to make sure that I'm not going to mess anything up. And so with potassium bonding to nitrate, we have a +1 and a -1. So one of each is all that's needed. And silver bonding with chlorine, they're 1 plus and 1 minus. Now we can apply our solubility rules. And identify our state symbols. And so silver chloride is a solid, and so this would be a precipitation reaction. Next up, we have our sodium sulfide. Let's write out our ions. Calcium is in group 2, so it's 2+. Halogens are -1 when they form ionic compounds. So calcium bonds with chlorine, sodium bonds with chlorine. You can do either one first. One of each is all that's needed for both in order to have neutral ionic compounds. And then afterwards, I have to make sure I'm balanced. I'm going to need 2 sodiums, and then that would give me 2 chlorines, and then I would be balanced. Now I need to apply my solubility rules, and that one is aqueous. And the calcium sulfide is also aqueous. Did you catch that? Since both products are aqueous, there is no reaction. Here's some more practice problems for you for predicting the products. Go ahead and pause the video and try to do it yourself. Okay, you have some answers? Let's go over this. So, chlorine is a 1- anion, hydrogen is a +1 ion, hydroxide is a -1, magnesium is a 2+. This is going to follow our double displacement pattern, and you might have even noticed that it's an acid-base neutralization. So when I write out my products, I know that acid-base neutralization reactions always produce a salt and water. My salt will be magnesium bonded with chlorine. I have to watch it because my magnesium has a 2+ charge and my chlorine only has a 1- charge. That means I'm going to need 2 chlorines for every 1 magnesium. Then I'm going to balance, and then my other product is water. Salt and water. HOH is water. Water state symbol is a liquid, not aqueous. You can't have water dissolved in water. That's just water. It's liquid. It's aqueous. It's not aqueous. Magnesium chloride is aqueous. I'm getting ahead of my pen. Water is liquid. All right, for our next one, let's identify our ions. This is not, it does involve an acid, but it's just a double displacement reaction. We don't know what products will form yet. And so we have Pb2+, S2-, H+, SO4, 2-. H bonds with S, lead bonds with sulfate, lead and sulfate. Lead is a 2+, sulfate's a 2-, and so I just need one of each. And then H2S. Do you remember the state symbol of H2S? It's a gas. This is a gas evolution reaction. And then lead sulfate, I wrote down the state symbol as solid. All right, next up, we have our last one. We have H plus NO3 minus, and then that's the hydrogen carbonate anion and the sodium cation. Sodium will bond with nitrate. H plus ions will bond with the hydrogen carbonate anion. And so then we will have as our ion exchange products NaNO3, H2CO3. Oh, that's one of those ion exchange products. And so that's going to decompose into water and some gas. And so I need to rewrite my equation not as hydrogen carbonate or carbonic acid. I need to rewrite it as H2O plus CO2. CO2 is a gas, water is a liquid, and that one is soluble. Double check for balancing. I have 1 sodium, 1 nitrate on both sides, 2 hydrogens total on both sides, and so I think I'm balanced. Yep. Okay, our last type of reaction pattern are redox reactions. Redox reactions will get their own chapter later in the semester. Redox is short for oxidation reduction reactions. And so, unlike our double displacement reaction patterns, redox equations involve a change in oxidation state. That means the electrons are going to be transferred between reactants and products. I'm going to go ahead and save redox reactions for a whole different video because they deserve their own video.